Our fourth and final example subsystem in 3061 lib is that of a manipulator, or like an intake, we could think of it as. Um, Again, like all of the example subsystems in 3061 lib, it's just an example. It's not going to work with any physical mechanism without changes. It is loosely derived from Husky Robotics 2025 manipulator as part of Reefscape. Um, Couple interesting things that we're going to focus on in this example um, is that unlike the other three subsystems, this one makes use of a state machine to model a much more sophisticated mechanism. So we'll spend most of our time looking at the state machine piece. Some other interesting features is unlike, I think the only sensors we've used in the other example mechanisms are encoders, either external or built into the motors. Here we have some sensors, whether they're um, IR or LiDAR or whatever they happen to be, um, to detect the presence of a game piece. So that's different. And then also here we see examples of using filters to determine if a game piece is stalled against the hard stop, which is fairly similar to determining if the elevator was jammed that we saw with the elevator example subsystem. But we're going to see a slightly different example of that here. The other features we've seen in other example subsystems. So let's jump in. As always, the manipulator class extends subsystem base, has a reference to its hardware specific IO object, and creates its inputs object. We have the testing mode things that we always have before with the various tunables here in terms of controlling the voltage of the manipulator intake, however you want to think about it. We have states. So we're going to see the state machine soon. But we need to keep track of what is the current state and what is the last state it was in. We need to keep track of both the current state and the last state because if they're not the same, it means it's time to transition to a new state. So if state has changed and no longer matches last state, we need to make a state transition. We want to ensure when this subsystem starts that we do make a state transition. So we set the last state to the uninitialized state and the current state to the waiting for game piece, which will ensure that we transition out of uninitialized and into waiting for game piece. We have some timers here. Sometimes state transitions are triggered by a timeout occurring. So we use timer objects for that. So we'll see examples of that within our state machine. As I mentioned, we're going to use a single pole IIR filter like we did in the elevator example subsystem, but here we're going to use it to determine if the game piece is stalled against the hard stop. So maybe we want to make sure the game piece is indexed in a very particular way. We do that by stalling the game piece against a hard stop. So it's not enough just to use like our IR sensor. We want to make sure it's actually positioned exactly where we want it. Some state transitions are triggered by the driver or the operator via a button press of some sort. Um, and so we have an instance variable here to know when the button is pressed to release the game piece. As the comment specifies here, it's really important that triggers don't directly change the state of the state machine, but rather only within the state machine itself is the state changed. Um, and so you'll see how we handle that. And the reason for that is if otherwise it's possible that both the state machine and an external trigger could both be setting the state and we could miss a state transition and that could lead to problems. So we want to make sure everything happens in a very deterministic fashion. We do register a system check command as always. And then we have our state machine thing here. I wanted to include an example of a state machine in 3061 lib. Sometimes mechanisms are sufficiently complicated where it warrants having a state machine. Um, in Husky Robotics, we try to avoid coding a state machine unless we feel like we have to. We would much rather have a much simpler command-based approach than a state machine approach. Um, However, if a mechanism is sufficiently complicated, we found that this particular structure helps us in terms of creating a robust implementation of a state machine. We always start by drawing out the state machine, capturing all of the states, capturing the transitions between states, capturing as each state is entered and exited, um, what what the device, each device should be, um, in terms of like what's the voltage of this motor, for example. So we draw all of that out, and once we have it done, drawn out well, it's relatively straightforward using this approach to turn it into code. Um, let's take a look. So this is a simplified example of some sort of like an intake or a manipulator that's collecting a game piece. We will detect that a game piece is in the process of being collected by using our sensor. However, we don't consider it fully collected or indexed until it stalls against a hard stop, and then we have a way to release it later. We also have in here the ability that maybe that perhaps the game piece has become jammed and we're unable to collect it, and so we have a state to like eject that so we can like try again. We did not come up with all of this. This approach is modeled based on a Chief Delphi post about state machines. So we have this enumeration called state, and then we have these specific states here. But let's go to the end. So each state has an execute method. This method will be called every cycle, so in periodic, for as long as we're in that state. When we transition to a new state, we call the onExit method for the state we're leaving. Then we call the onEnter method for the state we're entering. So we'll see what that looks like as we go. All right, let's go up to the top here. So our first state, waiting for game piece. This is where we want to start. Our approach is that in the onEnter method, we always set all of the devices to whatever voltage we want them to have. We don't make any assumptions about what state we're coming from. We find it reduces complexity by always explicitly setting, for example, the voltage of all the motors involved on the onEnter. Now it's possible that maybe a motor was at, let's say, 5 volts. We go to onEnter, we set it to 0, and then in execute, we set it to 5 again. We're not even going to see that 0. So because this all will happen within the same periodic, it's just going to stay at 5 volts. But it keeps our lives a lot simpler where we don't make assumptions about the states we're coming from. We always explicitly set each device to whatever we want it to be when the state is entered. We haven't found much use yet for the onExit method. I don't think in this example there's code in any of them. But I do like the symmetry, and maybe in the future we will. All right, let's look at execute. So when we're in the waiting for game piece state, this method will run over and over again in periodic. And what we're going to do is we're going to update the LEDs to show that we're waiting for a game piece. That's good feedback for the driver. And then we will check to see if a condition has occurred where we should transition to a different state. One transition that's easy to forget about is that state transitions can happen when the robot is disabled. So for example, the robot is disabled, it's on the field, we're preloading a game piece before the match starts. We want to make sure the state machine reflects that. Preloading a game piece is going to be a little bit different than a normal collection of a game piece during a match. So here's where we handle that. If we're disabled and the manipulator IR sensor is blocked, then hey, we're preloading a game piece, so we're just going to transition to the game piece and manipulator state. All state transitions are done by calling the set state method on the manipulator subsystem and specifying the state we want to transition to. Otherwise, if we're not disabled, if the robot is actively in a match, and the manipulator IR sensor is blocked, then we want to transition to the indexing game piece of manipulator. You may recall, as I said earlier, just because the IR sensor is blocked doesn't mean we're done collecting the game piece. It just means we're in the process of collecting the game piece. All right, so let's see the next step. So let's assume that hey, the sensor got blocked. We're now in the indexing game piece of manipulator state. Here is that. On enter, what do we want to do? We want to set the voltage of the manipulator to whatever the collection voltage is. You'll notice that's the same as the on enter, which I kind of skipped over here in waiting for game piece. We also want to set the manipulator voltage to that voltage. So again, is this strictly needed because it would have already been at that voltage? No, but we like being consistent where we explicitly set the motor voltage um, in every on enter method. Other things that are done in on enter are resetting timers, um, restarting timers, and resetting filters. Okay, so we have a timer here to make sure we don't stay in this indexing game piece state for too long. It shouldn't take that long to collect the game piece. If it does, something went wrong, maybe it jammed, kick the thing out, and try again. We also have a filter here to determine when we've stalled the game piece against the hard stop. We want to reset that filter as we begin to provide values to it. All right, execute method. This happens every time, every loop. So leave the LEDs in the indexing game piece state, which is a different color than waiting for game piece. So the driver knows, hey, we're in the process of getting the game piece. If the manipulator IR sensor is blocked and the last value from the filter for the current, and we're using that single pole filter, or is it up here? Single pole IIR filter. If the last value is greater than our threshold, then we know we've stalled the game piece against, and it's time to transition to the game piece and manipulator state. But both of those things have to be true for that to happen. Otherwise, if the timer has elapsed, okay, we've been trying to collect this game piece for 2 seconds and we haven't, the game piece is somehow stuck. So we're going to go to a game piece stuck state instead. Okay. Let's actually look at that game piece stuck state next. So when we enter the game piece stuck state, we are going to set the manipulator's motor voltage to the eject voltage. So we're going to run it backwards, try to kick that jammed game piece out. We're going to restart a different timer that will determine when we leave the state. Okay, so that's our on enter. In execute, this will run over and over again. We'll set the LED state to ejecting game piece. We're checking if that timer has elapsed. So basically, we're just going to run that manipulator motor backwards for half a second to get rid of that game piece. And then once that's done, we're going to assume it's been ejected, and we're going to transition to the waiting for game piece state and try all of this again. Okay. So that's the game piece stuck. If instead we actually stall the game piece against the hard stop, we will then transition into game piece and manipulator. If the game piece is in manipulator and properly indexed, we want to set the motor voltage to 0. So we do that on enter. In execute, we set the LEDs to indicate we have the game piece. And then we check for things that could cause us to transition. What would cause us to transition? If the driver or operator presses the release button. Okay, so this is that instance variable we saw earlier. We'll see where it can be set to true in just a moment. But if it is true, we want to switch to the release game piece state, and we want to set this instance variable back to false. That's important. What is another reason that we could leave the game piece and manipulator state? Maybe the game piece isn't in the manipulator anymore. Maybe it fell out. Maybe we slammed into something and it got knocked out. Who knows? If the manipulator IR sensor is no longer blocked, we're not in the right state. We need to transition to the waiting for game piece state instead. Okay. But let's say the driver pressed the button. Where are we at? Here we go. Release game piece. On enter, we set the manipulator voltage to whatever the manipulator release voltage is. That's a tunable. And then in the execute method, we set the LED color appropriately. And we don't want to immediately leave this state because it takes a non-zero amount of time for the game piece to exit the manipulator. We don't want to go back for the waiting to game piece state until the manipulator IR sensor is no longer blocked. Okay. So we will wait till the game piece is truly gone before we transition to the waiting for game piece state. All right. And here's our uninitialized state, which we should never go into. All right, so those are all the different states and their on, enter, and execute methods. Let's see how the state machine itself operates. And it's all done inside of the periodic method. So even though we have a state machine, we still need to update our inputs. We still need to process our inputs. We still need to log whatever extra things we need to log, which in this case, logging the state's really important. So we're going to log whatever state we're currently in. We are using that filter. And so we need to make sure that we are updating that filter every cycle by invoking the calculate method and passing in the current, the state or current from the manipulator. We still have testing mode support. We have to be, this is written a little bit differently than we saw in the other subsystems. Because maybe we just want to run the voltage of the manipulator, which is fine. We're bringing that system up. Or we're trying different voltages for collection, ejection, release, whatever it happens to be. But we need to make sure that this run state machine method is in an else case, because we don't want to be running the state machine if testing mode is 1. Otherwise, this control is going to be fighting the state machine, and that's not going to work well. And as always, we have our record how much time it took to run through this periodic method. Let's look at run state machine, and then we'll come back to the other things. So here's the logic for the state machine. If the current state isn't the last state, that means we just asked for a state transition to occur. And so we'll invoke the onExit method on the previous state. We'll set last state to the current state because we're transitioning, and then we'll invoke the onEnter method on the new state. Okay, so here you can see how the onExit and onEnter is called. Regardless of whether we're changing states or not, we will always invoke the execute method on the state, the current state. So this is what runs our state machine. All right, other interesting methods. We have a reset state machine method here. For example, if we interrupt everything and we just want to go back to a known state, here, this method here, release game piece, this is the method that will be called in response to a trigger of some sort. The driver presses a button to release the game piece. It invokes this method. This instance variable gets set to true. And as you may remember, this is what causes the state transition when we're in the game piece and manipulator state to go to the release game piece state. So we might have some accessor methods so that other subsystems or other code knows what state we're in. Like, hey, are we indexing a game piece? It can check the state for that. Have we indexed a game piece? It can check the state for that. So on and so forth. So here's the method to directly set the manipulator voltage. This is and here's another cool example. When it comes to IR sensors, we like some redundancy. If an IR sensor were to fail, or if a mechanism was to become bent and it can no longer detect, or if anything goes wrong, it's nice if you have a backup, because if that sensor goes down, you could be done for the whole match. So when possible, we try to have primary and secondary sensors for things like this. And then somehow in our operator interface, we have a trigger where you can toggle between primary and secondary. So as we'll see in a moment, in the inputs class, we have both the primary and secondary that are logged. but based on the current setting of the trigger, we will return either the primary or the secondary to determine if the manipulator IR is blocked. So we always can log both, but we only use the one that is currently selected. So this is a nice way to do that. This is our system check command, just does some voltage checking, pretty basic. All right, let's look at the constants. The CAN ID of the motor, the digital ID of the primary sensor, the digital ID of the secondary sensor, backup sensor, gear ratios, inversions, different voltages, timeouts, current limits, things like that. All right, our IO class, relatively straightforward, at least compared to that state machine. Whether the manipulator motor is connected, the primary and secondary IR, stator and supply currents, temperature, voltage, the velocity. This is useful. I mean, we're not doing anything with velocity here, but sometimes it's useful to be able to see, for example, is the motor, if you apply this much voltage, it should have a certain rotations per second. If it's way off, maybe something is wrong. Maybe a bearing is about to fall. Maybe something's rubbing that shouldn't. Something, maybe a leading indicator of failure that's about to hit your manipulator. So it's helpful to be able to see that. Here's our hardware specific class. Very similar to what we saw before. Got a voltage out object. We have a reference to the motor and each sensor, so that's a little bit new. Our status signals, our debouncer for connected. We create our Talon FX object like we've seen before. Here's us creating digital input objects, that's new. Creating all of our status signals and registering them. Configuring manipulator motor. We do our current limits, sensor to mechanism ratio, inversion. Apply and check that configuration, register that hardware for possible failures. Update inputs. We use the debouncer to see if we're connected, grab everything from the status signal objects. You'll notice that, well, that's all comes from the motor, except here's where we're reading the IR sensors. You always have to sit down and check how your IR sensor works. We like the idea of thinking of that when the IR sensor is blocked, that's true. But the way the sensor works, it returns a true value when it's not blocked, for the sensors that we're using, at least historically, most of the time. So we invert them here so that things make more, and then we name our properties very explicitly so it's clear we're talking about it being blocked. Here's a method to directly set the voltage that we can use in testing, or in our different states. And that's it for the IO class. So kind of an interesting example where the IO class here is relatively straightforward. You may notice there's no system sim object at all. We're not doing modeling of this system in any particular way. Just, you don't always need to have a system sim object. It's useful if you're doing control of some sort, like we were in the other three example subsystems, but we're not doing any closed loop control here. We're just commanding specific voltages. So, all right, that is our final example subsystem.